Hi, my name is Sri Tulisram from Group 6. So today I'll be presenting about the introduction for our project. So let's discuss about our project. The PID stands for Proportional Integral Derivative. The PID control is depend on the feedback. The output result is measured and compared with the input result. If there's any difference between the output and the input result, a correction will be calculated and applied until it's in a perfect form. A PI can handle many processes to acceptable level but have a fine control. Overshoot avoidance, PID is what we needed. For P control, the difference between a set point and the measured value determines the correction factor for this type of control. The cons for P function are if the differences approach 0, so too does the correction, which does the result that the error never goes to 0. The I function solves the 0 problem by considering the cumulative value of the error. The higher the difference of the set point actual value, the bigger the correction factor calculated, which can cause the delay in response, hence leads to overshoot. To avoid overshoot, the D function is used. Next is the tuning process. The tuning process is to make sure the disturbance does not affect much of the process oscillation around the set point simulation. The tuning can be made manually determined by the adjustment of the PID value without making any serious implication to the process. The tuning process also can be made by using different type of methods. For example, auto-tuning and Ziegler-Nichols method. Auto-tune is a PID tuning method for a plant modeled in software, for example Simulink. When it is being selected, the controller activates an output. The calculation of PID settings is made after observing both the delay and the rate which the change made. The benefit of using auto-tune can be generate initial PID design that can be later refined with real-time auto-tuning. The next method of auto-tuning is Ziegler-Nichols method, which works by zero integral and differential gains. It will then raise the proportional gain until the system is unstable. In this assignment, further explanations and example of the system will be given. That's all from me. Thank you.
Assalamualaikum and hi, my name is Karun Aisha Natasha binti Hasni with matrix number DE20058. Today I am going to present about open loop system. So this is the block diagram for open loop system. As you can see, we didn't connect the sum to the scope, and we connect the scope with the step because we want to read the input graph and compare it with the output graph. So this is the value for transfer function that we are going to use. And first we use 1 as a value of gain. So let's run the block diagram. Double click the scope. So this is the output graph, the blue line, and the yellow line is for the input graph. Next, we change the value of gain to 7.5. We run the block diagram. And this is the latest output graph. Okay, next we are going to change the gain block with the PID controller. So this is the new block diagram. For the PID, we use the value of Ziegler-Nichols method that we had calculated. For P, the value is 4.5, I 4.557, and D 1.111. Okay. We run the block diagram. So this is the output graph. Okay, that's all from me. Thank you.
Assalamualaikum and a very good morning, Doctor. My name is Muhammad Fahmi bin Ahmadi with matric number CE 2010. Okay, in this video, I'm going to show you the briefly explanation about the Ziegler-Nichols method in our closed loop controller for our project. Okay, so this is our transfer function that we have choose for this project, which is 20 by s cube plus 15s square plus 10s, which is we have a third order transfer function. Okay, when we want to use tuning by using by Ziegler-Nicholas method, we have to start with the very small of a proportional gain, while we have to set another gain, which is ki and kd integrate and derivative equal to 0. Okay, and then we have to increasing kp, which is gain of the proportional, until the system achieve neutral stability. Okay, neutral stability in term of the graph or in term of the that's oscillation, which mean we have to find until the system achieve this table. Okay, after that, after we have find this we get the neutral stability of the graph or like the oscillation, we have to record the critical or the ultimate gain, which is ku, which is kp at neutral stability. We have to record this the ku, the value of the that we insert to get this stability, and then records the period of the oscillation, which means we have to record the period, which is t. Okay, the period of ultimate gain tu in second, so the unit is in second. Okay, and then we have to refer to this table to find the next of the calculation to be inserted in our block control system. So that's a briefly explanation about the Ziegler method. Okay, so thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Putra Hasan dan Zakobari. I'm the number CE2031. So today I will present about result and discussion for closed loop using Ziegler-Nicholas method. So as you can see here, this is our output graph for the closed loop using Ziegler-Nicholas method, and I will show my simile. Our closed loop block diagram using Ziegler method. After that, this is our output graph for Ziegler method, and as you can see, this is a stable one. The gain that we use is 7.5. So after did some measurements throughout the graph, we get period of oscillation is VCR is 1.975 second. As you can see here, is a value that we get from output graph. After that, we use formula to find ki value and also kd value. So this is our formula that we use to find it. So this is a result of a closed loop control using PID tuner. As you can see here, the result of the graph seems like not stable as it had a huge overshoot. And to reduce its when can enter by verifying the gain or by increasing the derivative gain. So the output graph of the control using PID tuner. So I will show my simile. So I will connect PID controller, and then change the value. So see here, so for the proportional it will be 4.5, will be 4.557, and the derivative 2.5. Okay. So where the value I get is from the formula that have been calculated. So here 4.55 and 0. So I run the simulation. So this output waveform after using PID control. So this is I get. So the result from the output graph will be it's not stable, but because of a huge overshoot. So to reduce it, one can take it by varying the gain or by increasing the derivative gains. So that's all from me. Thank you.
Hi and Assalamualaikum warahmatullahi wabarakatuh to Dr. Rosli. My name is Muhammad Fidal Ramli. My matric number is CE200076. I would like to present about the conclusion. To summarize, we use the MATLAB Simulink software to do all the system simulation. Furthermore, if we create a P, PI and PID controller, we can test the open loop system by tuning the controller using the Bose-Ziegler-Nichols technique and PID tuner Simulink. To assess the process, open loop respond to change in instrumental variable output. The regular Nichols open loop approach, also known as the process reaction method, has applied. The system reaction should be documented for this basic test, preferably on a plotted or computer. After determining the exact process response value, we simply plug into them the Ziegler-Nichols equation with a specific multiplier constant for a controller gain having either a P, PI or PID action. The Ziegler rules teach us about the benefit of PID controller, such as the system capacity to make a significant better modification. PID controller tuning is an engineering effort that requires the consideration of operational and economic objectives. The application of analytical method of define a variable range of P and I values, and the confirmation of performance recently over time after the tuning was last adjusted. This strategy will yield near optimal tuning based on operation objective while assuming safe operation, a cheap manufacturing cost. Finally, the number of trials need to be raised from the recommendation, and the finding cannot be described analytic formula. Thank you. Assalamualaikum.